I'm going to use a squiggly that's benzene ring. I just want to draw all these benzene rings. Okay? The squiggly is the benzene ring. Okay? You have an amine, and the nitrogen is attached directly to the carbon of the benzene ring. That's an orthopair director, lone pair on the connecting atom. Okay, alcohol. Ether. Amide, right? Now, in a minute, we're going to see there's a different way that an amide could connect to a benzene ring that it would not be an orthopair director, it would be a meta-director, actually. Okay? But if your amide is set up this way, okay? If your amide is set up this way, where the nitrogen directly attaches to the benzene ring, then the connecting atom is a lone pair. So it's an orthopair director. Okay. Ester. And same type of situation with an ester in that there are other ways that we can connect an ester to a benzene ring. Okay. But if it's connected with the oxygen of the ester, connected directly to the carbon of the benzene ring, i.e. that's the connecting atom, a lone pair, orthopair director. Or some carbon and it's just got a bunch of sigma bonds. Okay? Regular alkyl. All right. Okay. Now, how can we distinguish meta-directors? Okay. Well, if you identify the connecting atom, and that connecting atom is part of a pi bond, okay? Remember pi bonds versus sigma bonds, a double bond, blah, 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 okay? If the connecting atom is part of a pi bond, it's a meta-director. Take a look at the molecule that you guys are using today, okay? The connecting atom is a carbonyl. It's the carbon of a carbonyl. It's part of a pi bond. That's why it's a meta-director. Okay. Oh, wait. Yes. Okay. Yeah. Everything's okay. Right. All M directors, okay, have a pi bond on the connecting atom. Okay, let's take a look at the various possibilities there. Okay, functionalities. Aldehyde. Benzene ring. Connecting atom as a pi. Okay. Ketone. Ester. Carboxylic acid. Here's an amide again. Okay. But notice that and these all have their own pair, but they're not the connecting atom in these situations. Okay. Here's your ester, okay, where the connecting atom is not this oxygen, it's the carbon of the carbonyl. So it's meta-director. Same here with the amide. Okay. And very strong meta-director is actually nitro group. And a lot of times we just draw nitro groups like that. Okay, the Lewis-Dot structure of one of the resonance structures looks like this. Okay? It's a pi bond on the connecting atom. All meta directors. And this is our category today. Does that make sense? Okay. Last thing I want to do is I want to do two things. I want to explain why. Why is this? Why did Mother Nature or God or whoever decide that if a lone pair was a connecting atom, then it would be an ortho pair director, blah, blah, blah. Okay? The other thing I want to show you is I want to show you the mechanism of the reaction that you guys are doing today. So I'm going to explain why it's a meta director by showing you its mechanism. If you look back to when we did the generic electrophilic aromatic substitution, we noted that in the resonance structures there was a positive charge that, it's not the precisely accurate way to say this, but was moving around the benzene ring. Every time I do a new structure, the positive charge is in a different location. The key difference between orthopara directors and meta directors is where that positive charge lands. Okay? And more specifically, does that positive charge land on the carbon that connects chi? Okay? If the positive charge lands on the carbon that connects chi, okay, it's an orthopara director. Okay? It has to be by drawing the resonance structure. I'll show that to you in a second. And if the positive charge sort of skip over that connecting carbon from the benzene ring, it's meta director, like in our reactions. Okay, big hairy mechanism. Should we do black? But it's great. So, why? Today's reaction that is of a meta director. So this is methyl benzoate. And our reagents. Before I forget, our reagents in your book, it describes you mixing them. Here at HPU, your lab staff has gone through that trouble for you, so they are already mixed together. Okay. All right, and ends up in the meta position. Okay. Could also be here, but that's the same problem. Just pancake flip. Okay. All right. All right. The first thing that happens is actually a reaction between sulfuric acid and nitric acid. And this first step, it's kind of fun actually. It really highlights just what a crazy strong acid sulfuric acid is. Because sulfuric acid in the first step protonates nitric acid. It's so strong at being an acid, it forces nitric acid to behave as a base. Okay. All right. First step is nitric acid And there's, there's different ways that you could draw this part. I'm doing the way that is most commonly, and I believe is the way it's shown, or maybe it's not even shown in your textbook anymore. Getting soft. I'm not sure. But I'm drawing it the way that it's most commonly expressed. I don't love it, but I want to be consistent. What else is out there? Okay. So the sulfuric acid can protonate this guy. Okay. If it protonates it right there, then shoot, sorry. And then we get what I always call like anchored water. It's water that's anchored onto a molecule, which makes it a fantastic leaving group. It's probably chart on this section. With this fantastic leaving group, it can leave in a push-pull type of fashion. And then we get the key intermediate. Okay? And this is called a nitronium. That is our E+. Very strong E+. Very electrophilic. So electrophilic that it entices methyl benzoate to break its aromaticity. Okay? If I remember correctly, I didn't look at the worksheet for this lab this morning, but if I remember correctly, I think on the worksheet I asked one, in the beginning, show the nitronium. This is called a nitronium. You guys, no, this one over here. I think I asked in one place, show the nitronium generated. But after that, in subsequent mechanisms that you've got to draw, you got to draw a bunch of mechanisms for this lab. In subsequent mechanisms, I say, well, you can start with the nitronium. Just draw this and pretend it already got generated. Okay? Once you've demonstrated you know how it's generated, that's good enough. Okay? All right. By the way, let me just pause real quick, sorry, to remind you guys of just academic integrity and all that stuff, and I hate to insult everybody who would never even think about it and stuff, but this has been one of the labs that has tempted some people in the past and gotten people in hot water. You draw these mechanisms, it's painfully obvious if some person ends up taking it from a different person. So even if, and I go with it, take it, but I'm going to change this bond, I'm going to change this bond. They go to a lot of work. Probably could have just been dedicated to generating it in the first place. And anyway, it still is completely obvious and it's painful. Everybody gets upset. Mostly me. Or me most of all. Okay, anywho. Sorry for that.
Well, now I'm just offended.
Okay, I'm sorry.
Just kidding.
From now on, if I talk about academic integrity, I just want to make clear I'm not talking to Kira, okay? I'm sure I'm not talking to any of you, but I'm protecting that anonymous person out there who could fall, who's stressed out because of the semester, because it happens. Totally happens. I get it. I get why that happens. But I'm just telling you, if you gotta take it, you gotta take a bad grade, take it on the chin like I did. Many times. Too many times. Okay, so just like before, the pi bond can swing out kind of like a gate. It's going to abandon that carbon because we want it to end up on the meta position. I'm just going to switch to NO2. Okay, you can draw the resonance structure if you'd like. positive charge right there. Okay. 5 on, 5 on. We're going to our resonance structures now. Okay. So electrons are spread, better way to describe it, spread over to that position. Positive charge is there. Okay. See the different positions of the positive charges ending up? And then these electrons can come over here. All right, so notice that it avoided that atom, okay? The positive charge was never on that atom. What that means for the hybrid is there's a partial positive charge on that carbon, a partial positive charge on that carbon, a partial positive charge on that carbon, but there is no partial positive charge on this carbon. A partial positive charge on that carbon is destabilizing, is bad. Okay? So Mother Nature doesn't want to make this intermediate in the first place. Why is a partial positive charge on that carbon where my finger is, why is that bad? Thoughts? Is there any kind of partial charge here on this atom? (50-50) guess. Kira nods. Kira's nod is correct. Okay. What kind of partial charge is on that carbon?
Positive.
Again, 50-50 chance.
Positive.
Positive! Bat in 1,000. Okay? Alright, there's a partial positive charge on any carbonyl carbon. In part because oxygen is more electronegative than carbon, but also in part because these electrons sometimes pop up here. Sometimes pop up here. So there's a partial positive charge there. If you put a partial positive charge there, that's two partial positive charges on adjacent atoms connected to each other. That's no good. Mother Nature doesn't like that. Mother Nature doesn't like like charges near each other. Mother Nature likes opposite charges near each other, right? Okay. All right. It's what matters. Okay. Because we're almost done here. The E went meta. Okay, the E went meta because the positive charge avoids carbon next to the partial positive charge. This partial positive charge. Okay? It sort of leapfrogged it. Boop, 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 boop. Okay? You guys get it? You get it? Make sense? Yeah? Okay. All right, last thing we're going to do is we just want to, I want to draw some quick pictures, nothing quite that elaborate. I want to draw some quick pictures on, well, why the orthopara? That makes some sense, hopefully. But why orthopara? It turns out, in the case of orthopara, having a positive charge right there is good. That's weird. It's good because the atom that it's connected to, that carbon it's connected to, it's a positive charge, has a lone pair, right? That's what we put it in that class, has a lone pair. And that lone pair actually can create a fourth resonance structure. They, for like 1 week, they got purple pens. I've been here 12 years, I've never had purple pens before, and I looked at it and I was so excited that this is like the last of my purple pen. It's dying. Okay, anyhow, sorry. Why would an OP director, this is a very terrible sentence, but it's brief, which is the point. Hopefully it works. Oh. And to show it to you, what I'm going to do is I'm going to take methyl benzoate and I'm just going to change it ever so slightly. I'm going to switch the position of the oxygen, making it an orthopara director. Okay? The methyl benzoate, it's like flipped. Or that oxygen is over connected to the CH3 that I haven't drawn here. Okay? And I'm going to use E+. I'm not going to use nitronium, just all for brevity. It'll go to the para position too, but I'll just show you. I'll just show it to you the ortho position. Same temperature. Okay. All right. So we've got an E+ here, and I'm going to swing out, connect it to the ortho position, abandon that carbon. Okay. Now let's start looking at the resonance structures. Okay, we come there. Charge moves there. These electrons will go there. And now, oh, screwed it up. Now, they are on the carbon that connects to the connecting atom, which has a lone pair. Okay. But it's no longer bad because these lone pair can actually come down here. And you get a fourth resonance structure, spreading that positive charge even farther out. The more Mother Nature can take charge and spread it around, the happier she is. Probably not the dominant resonance structure. Okay, it does put a positive charge on oxygen, that isn't great. Okay, but it's a resonance structure, a reasonable resonance structure nonetheless. Okay, so that adds stability. Does that make sense? And by the way, remember that weird, and alkyl groups. Remember, alkyl groups can stabilize a carbocation. That's why a tertiary carbocation is so much more stable than a secondary carbocation. Primary carbocations don't exist. Okay? Well, if there's an alkyl group right here, it stabilizes that carbocation just in the same way it does on any carbocation. Okay? Make sense? Okay, that's it, guys. Let me talk just a tiny bit about the setup and everything. We're pretty much doing it until the recrystallization. We're doing it pretty much like it is straight out of the book. Okay? But we are going to flame dry the key pieces. Okay. We have our bowls again. I think in all the sections we had, we burned themselves last week. So let's keep up that one.
Now you just jinxed it.
What's that?
Now you just jinxed it.
students find about when they burn themselves is that I will make them sit there at a sink for 15 minutes with their hand under the water.
You should
Wanna get-
have mustard in here.
I should
If you
what?
put Mustard. If you put mustard on and burn with vinegar.
A mustard?
Yes, you should have mustard in here.
That's gotta be an old wives' tale.
No, I used
Mustard?
Yeah, because I burned
Does it have to
myself.
be, does it have to be like Dijon or can it be yellow or honey?
I used it on a
I'm gonna Google this, Kira.
So,
Googling this as soon as we're done.
do it.
All right.
Challenge
I
accepted.
owe you a donut if you're right.
Okay. I'm down with that.
Oh yeah. Oh yeah, I do have one. Okay. I guess, yeah, we are just flame drying 4 things, okay? Put the stir flea inside the conical vial, all right? As always, Bunsen burner, bowl on one side, unflame dry stuff on the other side. I don't have the 4th thing. The 4th thing is one of those real small little test tubes, okay? You guys all know how to flame dry. Hair needs to go back, all that good stuff, okay? And then, you know, look for the fogging and everything like that. As soon as the fogging's done, you put it in the bowl, so forth and so on, okay? The reaction has you, you're going to use your 250 for an ice bath, okay? Only make this about an inch high, okay? Only an inch high. You don't want to, what students will sometimes do is they'll make these ice baths, okay? Don't forget the blue nut and then the O-ring, okay? Maybe I'll just show you this setup real fast. That might be a good idea. Students will sometimes, they'll have the ice bath like to the very top of the thing, and then it's not stirring because it's so far away, and so they just submerge this underwater. And that blue nut in the O-ring, it's probably a good seal, but water can go in. So you just need, you know, an inch of ice bath, okay? These differences that we're talking about, okay, this makes the energy of activation for orthopara lower because of this 4th structure. Okay? Differences in energy of activation disappear the warmer the reaction is done. Now everything's colliding with lots of energy. That's why we do this at 0 degrees. We did it at room temperature, we'd probably get a mix of meta and ortho and stuff like that. Okay, does that make sense? And then you've got your mixture of your nitric acid, sulfuric acid in the small little itty bitty test tube, okay? And the small little itty bitty test tube with this incredibly corrosive mixture is in what? It's in a beaker, right? We always keep that kind of dangerous stuff in beakers so it doesn't tip over, okay? And then when we go to add it, you want to hold that beaker with the test tube right next to the mouth of this. You don't want to hold it over here and dribble sulfuric acid, nitric acid all over the place, okay? And you're going to use a long pipette and add it carefully directly down the air condenser. Does all that make sense, guys? Questions? Let's do it to it.